Let's start with something we all experience: heating wires. Have you ever noticed that a bulb glows brighter after a few seconds? That's because its resistance changes with temperature. In physics, we describe this using a property called resistivity, which changes as temperature changes. For most metals, resistivity increases with temperature. For semiconductors, the opposite happens: resistivity decreases when temperature goes up. In the graph shown, you'll see two different curves, one rising for metals and one falling for semiconductors. That's the key difference. Now let's understand this behavior with an equation. We define resistivity at temperature T using the formula rho sub T equals rho naught multiplied by open bracket 1 plus alpha multiplied by open bracket T minus T naught close bracket here. Rho sub T is resistivity at temperature T, rho naught is resistivity at reference temperature T naught, alpha is the temperature coefficient of resistivity. Alpha tells us how sensitive a material's resistivity is to temperature. It is measured in per degree Celsius or per Kelvin. For metals, alpha is positive, so resistivity increases with temperature. Some materials behave differently. Alloys like nichrome, manganese, and constantan have a very small temperature coefficient. That means even when heated, their resistivity remains nearly constant. In such cases, alpha is almost zero. Because of this, these alloys are used in applications where precision and thermal stability are important, like resistors or heating wires in electric appliances. In the resistivity versus temperature graph, the curve for nichrome is almost flat. Semiconductors, like silicon and germanium, act in the opposite way to metals. As temperature increases, more charge carriers become available in semiconductors. This leads to more current flow and hence lower resistivity, even though collisions also increase. That's why the resistivity of semiconductors decreases with rising temperature. In the graph, the curve for semiconductors slopes downward sharply, showing this drop in resistivity. Let's now understand this behavior from the microscopic point of view. Resistivity is given by the formula rho equals m divided by open bracket n multiplied by E squared multiplied by tau close bracket, where m is the mass of an electron, n is the number of charge carriers, E is the electronic charge, tau is the mean free time between collisions. In metals, n is constant and tau decreases with temperature, so resistivity increases. In semiconductors, n increases rapidly with temperature. This outweighs the decrease in tau, so resistivity decreases. Let's solve a real-life problem. Suppose a nichrome wire has resistance R1 is equal to 75.3 ohms at 27 degrees Celsius, current I is equal to 2.68 amperes, voltage V is equal to 230 volts, and alpha is equal to 1.70 into 10 to the power minus 4 per degree Celsius. What is its final temperature when it stabilizes? Step 1. Find final resistance R2. R2 is equal to V divided by I is equal to 230 divided by 2.68 is equal to 85.8 ohms. Step 2. Use the temperature resistance formula. Step 2. Use the temperature resistance formula. We apply the equation R2 equals R1 multiplied by open bracket 1 plus alpha multiplied by open bracket T to minus T1 close bracket, substituting the values 85.8 equals 75.3 multiplied by open bracket 1 plus 1.7 into 10 to the power minus 4 multiplied by open bracket T to minus 27 close bracket. Solving this, we find T2 is approximately equal to 847 degrees Celsius. This is the steady operating temperature of the nichrome wire in the toaster. Let's quickly recap what we've learned. Resistivity increases with temperature in metals due to more frequent collisions. In semiconductors, Resistivity decreases because more charge carriers are released. Alloys like nichrome maintain almost constant resistivity, great for stable heating. The formula we used was rho sub T equals rho naught multiplied by open bracket 1 plus alpha multiplied by open bracket T minus T naught close bracket. Understanding how resistivity depends on temperature helps us choose the right materials for heating elements, electronics, and precision devices. See you in the next session, where we'll explore electric power and energy in circuits.